"Houston, we've had a problem." Those four words crackled across 200,000 miles of space on April 13, 1970, marking one of the most harrowing moments in human exploration. Apollo 13's oxygen tank had just exploded, transforming what should have been NASA's third lunar landing into a desperate fight for survival. Three astronauts, Jim Lovell, Jack Swigert, and Fred Hayes, suddenly found themselves hurtling through the void in a dying spacecraft, with mere hours of power remaining and the cold vacuum of space waiting to claim them. But imagine for a moment that this same catastrophic failure happened today. Picture Apollo 13, launching not in 1970, but in 2025, equipped with artificial intelligence that never sleeps, materials that heal themselves, and communication systems that transmit data at the speed of light. The story that unfolds might fundamentally change everything we thought we knew about that near disaster. The first critical difference would have emerged in the seconds immediately following the explosion. In 1970, confusion reigned as engineers scrambled to interpret garbled telemetry while the crew struggled to understand what had just torn their spacecraft apart. Precious minutes ticked by as human minds worked frantically to piece together the puzzle of cascading system failures. A modern spacecraft would have responded differently. NASA's 2024 AI Use Case Inventory highlights the agency's commitment to integrating artificial intelligence in its space missions and operations, ranging from AI-driven autonomous space operations to advanced data analysis for scientific discovery. An AI system aboard the spacecraft would have diagnosed the oxygen tank failure within seconds, immediately identifying all affected systems and automatically initiating contingency procedures. This AI wouldn't think like a human. It would process thousands of failure scenarios simultaneously, cross-referencing them against the actual damage pattern in milliseconds. While the 1970 crew spent critical hours figuring out they needed to abandon the command module for the lunar module, the AI would have recommended this course of action almost instantly, calculating exact power consumption rates and predicting consumables usage down to the minute. But artificial intelligence represents just the beginning of how modern technology would have transformed this crisis. Lockheed Martin is already using AI for spacecraft monitoring and control, with AI applications on board satellites that have the ability to predict potential failures faster than humans, allowing controllers to stay ahead of issues before they occur. In fact, such predictive systems might have detected the developing electrical problems in Apollo 13's oxygen tank hours or even days before the explosion occurred. The life support crisis that nearly killed the crew reveals perhaps the most dramatic technological advancement. Apollo 13's survival came down to consumables, oxygen, water, power, and most critically, carbon dioxide removal. The crew had to jury-rig a CO2 scrubber using duct tape, plastic bags, and cardboard from their flight manuals. It was brilliant human engineering under extreme pressure, but desperately primitive by today's standards. The CCTARS provides 7 primary spacecraft life support functions in a highly integrated and reliable system: air temperature control, humidity removal, carbon dioxide removal, trace contaminant removal, post-fire atmospheric recovery, air filtration, and cabin air circulation. Modern spacecraft don't just consume resources, they regenerate them continuously. Approximately 90% of water is recycled on the ISS, demonstrating how closed-loop life support systems can dramatically extend mission duration. If Apollo 13 had carried today's environmental control and life support system, the CO2 crisis that nearly suffocated the crew would never have existed. Modern regenerative carbon dioxide removal systems operate indefinitely, automatically regenerating their scrubbing capacity by heating special materials to release captured CO2 into space. The famous square peg in a round hole problem would have been irrelevant. Water scarcity represented another life-threatening challenge for the historical crew. They faced severe dehydration because they had to ration their limited water supplies to preserve what little they had for cooling electronics. A modern spacecraft would have recycled not just humidity from the air, but even the crew's urine, providing an essentially unlimited water supply for both drinking and cooling systems. Even the physical damage itself would have been managed differently. The explosion that created a hole in Apollo 13's service module, venting precious oxygen into space, might have been contained by self-healing materials that can repair themselves automatically after damage. These advanced materials contain microscopic capsules filled with healing agents that activate when the material is damaged, potentially sealing small breaches without human intervention. Communication represents another revolutionary advancement. One of the most agonizing aspects of the Apollo 13 crisis was the limited contact with Earth. Mission Control could only talk to the crew intermittently through crackling radio transmissions, and data transfer was painfully slow. Critical information took hours to relay. NASA's Deep Space Optical Communications Technology demonstration broke yet another record for laser communications by sending a laser signal from Earth to NASA's Psyche spacecraft about 290 million miles away, with data rates 10 to 100 times higher than radio frequencies. If Apollo 13 had been equipped with today's laser communication systems, Mission Control would have maintained continuous, high-definition video contact with the crew throughout the crisis. This transformation goes far beyond better communication. It fundamentally changes crisis management. NASA's laser communication systems can transmit at 1.2 gigabits per second, enabling live ultra-high-definition video feeds between astronauts and Earth. Mission Control could have seen exactly what the crew was seeing, guided them through complex procedures with visual overlays, and transmitted detailed three-dimensional models directly to the spacecraft's computers. The famous improvised CO2 scrubber could have been designed and tested virtually on Earth, then transmitted as precise assembly instructions with augmented reality guidance. Instead of the crew working from hand-drawn sketches and verbal descriptions, they could have followed step-by-step holographic instructions overlaid on their actual workspace. Moreover, this communication revolution enables something impossible in 1970: distributed problem-solving. NASA's terabyte infrared delivery achieved record-breaking transmission rates of 200 gigabits per second, sufficient to return over 5 terabytes of critical science data in just 3 minutes. With this bandwidth, every piece of telemetry from Apollo 13 could have been transmitted in real time, allowing ground-based AI systems worldwide to work in parallel with the spacecraft's onboard intelligence. Instead of just NASA's Houston Mission Control working on the crisis, engineering teams in Munich, Tokyo, Moscow, and Bangalore could have contributed simultaneously, creating a global brain trust focused on bringing the crew home. The collective intelligence of human civilization would have focused on solving the problem. The spacecraft design itself would have incorporated fundamental differences in redundancy and resilience. Apollo 13's near-catastrophic failure stemmed from a design philosophy where weight savings often trumped backup systems. While the spacecraft had some redundancy, the oxygen tank explosion cascaded through multiple systems simultaneously. Modern spacecraft like NASA's Orion incorporate extensive redundancy systems. 4 identical solar panels that can each operate independently. 4 main batteries, where any 2 can get the vehicle home, and built-in redundancies in thermal control cabin, pressure oxygen, and CO2 controls and water systems. Today's spacecraft are designed with graceful degradation, the ability to lose multiple systems and still complete the mission safely. Instead of losing all oxygen when one tank exploded, a modern spacecraft might have 6 smaller oxygen tanks distributed throughout the vehicle, making total system failure virtually impossible. The power crisis that forced the crew to live in near-freezing darkness would have been prevented by nuclear power systems that provide continuous electricity for decades, without requiring any consumables. One of the most constraining factors for Apollo 13 was electrical power. The fuel cells that provided electricity required oxygen to operate, and when the oxygen was lost, so was most of the spacecraft's power. The crew was reduced to conserving a few hours of battery power for the critical re-entry phase. Lockheed Martin is developing nuclear thermal propulsion, nuclear electrical propulsion, and fission surface power for faster, more efficient spacecraft travel, with nuclear systems offering increased efficiency, reduced fuel consumption, and longer mission durations. If Apollo 13 had carried a modern nuclear power system, the electrical crisis would have been irrelevant. Radioisotope thermoelectric generators provide continuous power for decades without requiring any consumables. Nuclear power systems also generate heat as a byproduct, solving another dangerous aspect of the crisis. With power systems shut down, Apollo 13's temperature dropped to near freezing levels, threatening the crew with hypothermia and risking critical system failures. A nuclear-powered spacecraft would have maintained comfortable temperatures throughout the crisis, eliminating the crew's suffering from dehydration, hypothermia, and the psychological stress of living in a slowly dying spacecraft. The medical and psychological aspects of the crisis would have been managed entirely differently as well. The Apollo 13 crew endured 4 days of uncertainty, fighting cold, dehydration, and exhaustion while not knowing if they would survive. Modern spacecraft would include AI systems designed not just for technical support, but for psychological support, monitoring crew stress levels and automatically adjusting the environment to optimize mental health. High-bandwidth laser communications would have allowed the crew to maintain regular video contact with their families throughout the crisis. Instead of brief, formal communications with mission control, they could have had private conversations with loved ones, providing crucial emotional support during their ordeal. Perhaps most remarkably, modern spacecraft carry 3-dimensional printing systems that can manufacture tools, spare parts, and even medicines on demand. NASA's 2024 research announcement focuses on flight investigations, seeking to demonstrate space-based manufacturing and production activities of advanced materials or technologies only attainable in microgravity. If the Apollo 13 crew had needed a specific tool to implement their improvised solutions, they could have simply printed it from raw materials. When we consider all these technologies working together, the true transformation becomes clear. A modern Apollo 13 crisis would unfold dramatically differently from the historical version. When the oxygen tank exploded, the spacecraft's AI would immediately diagnose the failure and begin implementing contingency procedures. Laser communications would provide mission control with real-time video of the damage and complete telemetry data. Engineering teams worldwide would be immediately brought into the response, with AI systems on Earth running millions of simulations to find the optimal path home. The spacecraft's modular design would allow the damaged service module to be jettisoned safely, with backup systems taking over its functions. Instead of the desperate scramble to keep the crew alive that characterized the historical mission, the modern crew would remain comfortable and safe. Nuclear power systems would provide unlimited electricity. Regenerative life support systems would eliminate the CO2 crisis. Advanced materials would contain the damage to non-critical systems. The AI would calculate multiple return trajectories and continuously optimize the path home. Ion propulsion systems would make gentle course corrections automatically. Engineers on Earth would identify improvements to the spacecraft systems and transmit new software to optimize performance. Instead of the nail-biting uncertainty of the historical re-entry, the return would become almost routine. Multiple backup systems would ensure redundancy for every critical function. Real-time telemetry would allow precise monitoring of all systems. The crew would arrive home healthy, having turned a potential disaster into a demonstration of engineering excellence. This transformation represents more than just technological advancement. It represents a fundamental shift from heroic improvisation to systematic resilience. The historical Apollo 13 required extraordinary courage and brilliant improvisation from both crew and ground teams. They succeeded through determination, creativity, and more than a little luck. A modern Apollo 13 would succeed through systematic redundancy, predictive intelligence, and advanced engineering. This doesn't diminish human courage or ingenuity, it amplifies them. Instead of spending all their energy on basic survival, a modern crew could focus on scientific objectives, system improvements, and turning the crisis into an opportunity for discovery. The technologies that would have saved Apollo 13 aren't science fiction, they exist today, flying on missions throughout the solar system. Laser communication systems are transmitting data from Mars. Advanced life support systems operate on the International Space Station. AI systems guide rovers across alien landscapes. Nuclear power systems enable missions to the outer planets. Apollo 13 taught us that space exploration requires not just courage and skill, but robust engineering, careful planning, and the ability to adapt when things go wrong. The technologies of 2025 embody those lessons, creating spacecraft that are not just capable of reaching their destinations, but of surviving and thriving when the unexpected occurs. The crew of Apollo 13 proved that humans can overcome seemingly impossible challenges through ingenuity, determination, and teamwork. Today's technology doesn't replace those human qualities, it amplifies them, creating possibilities that the Apollo generation could barely imagine. When we combine human creativity with advanced tools, when we build networks of knowledge spanning the globe, when we design systems that learn and adapt, we create foundations for achievements that no single technology or individual could accomplish alone. Failure is not an option was the motto that saved Apollo 13 in 1970. Today, we might say instead, failure is not a crisis, but an opportunity to demonstrate the resilience, redundancy, and adaptability that define truly advanced space exploration. The universe is waiting, and we're better prepared for it than ever before.